Integrating a function, otherwise known as finding the antiderivative. In fact, that may be more descriptive. The integral of a function gives the area under the function's curve. In this sense, this use of area, we consider area below the horizontal axis to be negative. So we can have a negative area in this context. The theory is we approximate the area on a curve with narrow rectangles that have one upper corner or lower corner if we're going below the axis on the curve and one side of the rectangle on the axis. We take the limit as the width of these rectangles along the axis gets close to 0, and we get a good approximation of the area under the curve. Doesn't matter if the curve is completely under the rectangles or if the rectangles are inside the area of this curve. When we get those little narrow rectangles, we fill in just about perfectly, and when we take the limit as the width goes to 0, we get the area under the curve. Well, that is the theory. The practical way to take an integral, other than with an infinite number of limits, or the antiderivative, is to find a function whose derivative is the function being integrated. The symbol for an integral of a function, f of x, is this symbol, f of x dx, where the elongated s, which is this symbol, indicates the sum of rectangles, and the differential dx indicates the arbitrarily small increment, which has its roots in the small width of the rectangles being summed. So this was the integral dx acts as parentheses. So think of the parentheses starting here and ending here. And the integrated function is whatever is between the two parts of the symbol. We can work on parts of the sum or difference of an integral. The integral of a f of x plus b g of x dx is a integral f of x dx plus b integral g of x dx. Now it's a difference here, and this is a sum symbol, but remember in algebra, we do not really subtract, but we add negative numbers, so b can be negative, and then we're essentially doing the subtraction. It is very important to recall that the derivative of a constant is 0. Now we're going to find the integral x cubed dx. The derivative of x to the fourth is 4x cubed. And by the time you get to integrals, you should know the derivative of x to the n. So the antiderivative of x cubed must involve x to the fourth. But there's the issue of the 4. This leads us to the equation integral x to the n dx equals 1 over n plus 1 x to the n plus 1 plus c. Remember, we just decided that the derivative of c is 0, so we don't know which constant might be added to this part of the function. And we have to restrict this rule here that x not equal negative 1. If it's negative 1, we're going to end up with a logarithm, and that's another time. The constant c is needed because the derivative of any constant is 0. So the integral of x cubed dx is 1/4 x to the fourth plus c. And if I check this, the derivative of 1/4 x to the fourth plus c is 1/4 4 times x cubed plus 0 equals x cubed. The integral of sine x dx is negative cosine x plus c. By the time you get here, you should have had the derivative of the sine of x is cosine, and the derivative of the cosine x is negative the sine, which is why the negative sign is going to be coming in. The integral of e to the x dx is e to the x plus c. This is a nice special function. E to the x is its own derivative and hence its own integral, except for that plus c. The reason is the derivative of e to the x is e to the x. The definite integral, integration over an interval. We don't always want an indefinite integral over an area on the curve that goes on to infinity. To find the integral over a specified domain, evaluate the integral at the upper or the right domain value of interest and subtract the integral at the lowest or the left domain value of interest. Note that the constant of integration cancels out with the subtraction. So if we got a plus c and then we got a minus plus c, we don't have to worry about that constant of integration with definite integrals. So I'm going to find the integral from 1 to 4 of f of x equals x to the negative 1/2 power. Well, that's x to the n. N doesn't have to be an integer. So we write it like this. The integral from 1 to 4, x to the negative 1/2 dx. And so negative 1/2 plus 1 is positive 1/2, so we get x to the 1/2 over n plus 1, 1/2, from 1 to 4. So we flip this over, we get 2x to the 1/2 from 1 to 4. So we take the upper limit, 4. The square root of 4 is 2. 2 times 2 is 4. Take the lower limit, 1. Square root of 1 is 1. 2 times 1 is 2. So 4 minus 2 is 2. So the area under this curve from 1 to 4 is 2. A lot of times with integrals, the problem isn't as much with the calculus rules as with the algebra. So if I want to find the area of the curve, f of x equals 2x plus the square root of x over the cube root of x from 1 to 3, and that dx should not be there. I would look at this. The integral from 1 to 3, 2x plus the square root of x over the cube root of x dx. Well, this is going to look like this. We're going to write this in what I call friendly notation, which is exponents rather than radicals. So I have the integral from 1 to 3, 2x plus x to the 1/2 over x to the 1/3 dx, which is 2 integral 1 to 3 x to the 2/3, x to the first minus 1/3 is 2/3 dx, plus the integral 1 to 3 x to the 1/2 minus 1/3 x to the 1/6 dx, which is 2 x to the n plus 1, 5/3 over 5/3 from 1 to 3, plus here I have x to the 1/6 plus 1 is 7/6, x to the 7/6 over 7/6 from 1 to 3. And then we just plug in these values, 3 and 1, plug in the 3 and the 1, and we get this expression, which for our practical purposes here, we just assume that your calculator can just finish the problem. And this is fine place to conclude. I appreciate if you would hit the subscribe button at the bottom. Thank you for watching, and look for any of our other videos. They are quite a few.